Ellen gave the substantive background and started talking about M+ modeling, going quite far into the M+ DSEM modeling. I'm going to back up a little bit and look at some of the basic issues. The occasion for this workshop is that M+ version 8 came out April 20th. I know it well. It was a hectic day. So what was introduced then is time series analysis. You know, that term is usually reserved for n equals 1 studies, 1 unit varying across time. SMOG in LA used to be the common topic. And you know, BMDP T1 and T2, did anybody use those 20 years ago? Yeah, right. They were pioneers, but boy, was that hard to use. Linda Mutén was working there as a customer support person, and it crashed all the time. Now it works very smoothly in M+, but we are going to take more of an interest in the 2-level analysis, that is n greater than 1. And we're going to take a look at all these various random effects, that is coefficient parameters that vary across individuals, that Ellen started talking about. And the reason there are so many of them, so many more than in typical multi-level modeling, is that subject is on level 2. And anything that varies across subject has large variances. So we're going to have many more random effects, many more random slopes in particular, than we have in regular cross-sectional 2-level analysis. And the interesting thing is that TMR also managed to go into the cross-classified area, which is a generalization of the 2-level case where random effects vary not only across subjects but also across time. And that's really exciting. I'm going to give you some examples of that, particularly after the afternoon break. So try to hang in there to the end of today. So putting all of these techniques together and adding the general parameterization of structural equation modeling on top of that, we reach something that we call DSEM, dynamic structural equation modeling. Very general Lichtenberger modeling, so general that you really can only do it through Bayesian estimation. ML can be used for some special cases, but not the general cases that we're interested in. Statistical background that you can read about is this one that I pointed to before. It sits on our website there in the left margin. And I should tell you that tomorrow morning, you're really going to get the statistical background, the heavy-duty tech stuff for the methods-oriented people in the group. TMR is going to talk for 2 blocks, the morning and the early morning and the late morning. And if you want to follow that, you better take a look at this paper tonight, not night reading. Should put you to sleep right away. After the coffee break, TMR will become a little bit more applied, applied in the TMR sense. But he's actually going to demonstrate the program, doing a little plot demonstrations for you. So it's going to be fun. There is actually another paper here, the mixture version of all of this. And the paper is out, even though the program is not out. Some bits and pieces of it exist in TMR's laptop, you know, the one that you can look at for a fee. And whereas this exists in M+ version 8.0, but the paper has not been published, so a little bit upside down world here. The user's guide, as you saw as you entered, it has now gotten quite thick, adding n equals 1 examples in chapter 6, in the growth and survival chapter, and n greater than 1 examples in chapter 9, the multi-level chapter, with many parts to each example, basic and advanced versions of the setups. There's quite a lot of new stuff there. And also the web page has been added for our website, the special web page for this topic. So let's see. I'm going to use Ellen's style of outline here again, which works pretty well. So what we're going to do now is take the step back and try to figure out what's in this black box of Bayesian analysis. Because, you know, sure, you can say estimator equals Bayes, but wouldn't it be fun to know a little bit more about what's happening and be able to use it in more smart ways? So I'm going to talk about that and talk about an introduction to longitudinal analysis and n equals 1 time series analysis. And right about here is where we're going to have the break. I'm probably going to get into 2-level a little bit, But the goodies, I'm going to save, the really exciting things I'm going to save for after the coffee break. So, this is an extended version of what I said yesterday in the mediation workshop, but I'll pretend that you never heard this before. Good stories worth telling twice, at least twice. Okay, so we have a new estimator here. Instead of the standard estimator that we are used to, like ML, we're going to go to Bayes. And we're going to talk about the advantages of Bayes over ML. We're going to talk about an example, discuss what we mean by convergence. We're going to show various kinds of new plots, and talk about how long this takes in M+, and give you some suggested readings. Here you have it. The 6 points that I can think of as reasons for why you would be interested in Bayes over ML. ML is an example of so-called frequentist analysis, which is often a polar opposite of what Bayesian analysis is about, at least according to those who fight for both sides. I would argue that Bayes can be used to learn much more about parameter estimates, first of all. In ML, you usually strive for getting a good parameter estimate, one parameter estimate, and a standard error for that. Sometimes you want more than that, but that's a standard approach. In Bayes, you get the whole distribution of the parameter estimate. Whole distribution, not only the mean and the variance or standard deviation or standard error, but the whole distribution, so that you can create percentiles low and high to get confidence interval around the estimate. You can do something similar to that with ML by using bootstrapping, but of course that's an additional step in maximum likelihood, which sometimes can be a very time-consuming step. Another advantage is that we don't need the large sample theory that ML builds on. You know, we have the estimate, which in large samples at least has a approximately normal distribution, for which confidence intervals that are equal to the parameter estimate plus minus 1.96 times the standard error. That symmetric interval would be relevant because we believe that the parameter estimate has this approximate normal distribution, which is a symmetric distribution. You don't need that. You don't need that large sample theory, because Bayes makes no assumption that the parameter estimate distribution is normal. And in fact, it can often be quite non-normal. As we know from yesterday, the indirect effects, for instance, can be very non-normal, skewed in various directions. Particularly, I would say, when the outcome is not continuous, when y is a binary or count. Small sample performance can be better with Bayes, at least if you use what's called weakly informative priors. And like I said yesterday, I played around with that in 2010 in a working paper that sits on the website under the papers, Bayesian analysis, at the very bottom of that. Particularly for two-level data where you have a small number of level 2 units, small number of clusters, maybe even go as low as 10. You can perhaps do better with Bayes over ML. And then this important point that analysis are in some cases much less demanding computationally. For instance, when maximum likelihood requires numerical integration, which is, as an example, happening when you do item response theory. You have a continuous latent variable, the trait, as it's called, and you have, say, binary right-wrong answers as factor indicators or trait indicators. That combination of continuous latent categorical observed gives rise to the need for integrating over the factor so that you describe the marginal distribution for the observed items. That numerical integration gets very heavy if you have many factors, perhaps already with 4 factors or 5 factors. Although you can get up to higher number of factors, like 7, 8 perhaps, but the computing time goes up very quickly, and the precision of the estimates and the log likelihood goes down very quickly. Bayes has no such problems. And that's why we can work with so many complex models. Bayes has no is not inhibited at all by the number of dimensions, or very little. And in fact, maximum likelihood, point number 5, becomes impossible in many cases. And Bayes can then be looked at as a computing algorithm that would give essentially the same results as maximum likelihood if maximum likelihood was computationally feasible. So in large samples, and with Bayes using non-informative priors, we're going to say what that is shortly, you would get almost the same result with Bayes as you would have with ML if you've been able to compute it. Which means that new types of models can be analyzed with Bayes, which were impossible for ML. And DSEM, the topic of today and tomorrow, is a very good example. There are many other good examples, but that's a good example. Some DSEM models, particularly those without random effects, can be done by ML, but not the general ones that we're going to look at today. So, there you have it. Are you motivated? Okay.